Okay, let us begin with lecture 13, a continued discussion on conditional expectation. Let's start with section 1. Conditional expectation conditioned on a random vector. Consider a random vector x which maps from our sample space omega to Rn, defined on a probability space omega script f p. Recall that the projection P sub I mapping from Rn to R of an n-dimensional vector x onto its ith component gives us x sub I equals Pi sub I of x. This projection is a Borel measurable function. It follows that x sub I, which is Pi sub I composed with x, is a random variable for each I from 1 to n. Further, the event space generated by the random vector x, denoted sigma of x, is given by the sigma algebra generated by its components x1, x2 all the way up to xn. As a reminder, if we have an n-length sequence of events, ai in script f for I from 1 to n, then the vector x formed by the indicator functions of these events, indicator ai for I from 1 to n, is a random vector. The smallest event space generated by this random vector x is sigma of x, which is the sigma algebra generated by the events a1 through an. Now for the definition of conditional expectation given a random vector. Consider a scalar random variable x mapping omega to R such that it's integrable, meaning the expectation of its absolute value is finite, and let y be a random vector mapping omega to Rn for some natural number n, both defined on the same probability space omega script f p. The conditional expectation of the random variable x given the random vector y is defined as the conditional expectation of x given the sigma algebra generated by y, that is the sigma of y. Next, let us look at a lemma on event spaces generated by sequences of random variables. The lemma states that for a random sequence x, which we can think of as mapping our sample space omega to the space of real valued sequences Rn, defined on our usual probability space omega, script fp, we have the sigma algebra generated by the first n components, that is sigma of x1, x2 up to xn is a sub-sigma algebra of, or is contained within the sigma algebra generated by the first n plus 1 components, sigma of x1 up to xn plus 1. This holds for any natural number n. Essentially, adding another random variable to our collection can only make the generated sigma algebra larger, or keep it the same, it never shrinks. Now for the proof, consider any vector x in R to the n plus 1. Any generating event for the collection sigma of x1 through xn is typically of the form of an intersection of events where each xi is less than or equal to some xi. That is the intersection from I equals 1 to n of the pre-image under xi of the interval minus infinity to xi. This event can be rewritten by intersecting it with the pre-image under xn plus 1 of the entire real line R. Of course, the pre-image xn plus 1 inverse of R is just the entire sample space omega. So intersecting with it doesn't change the event. However, writing it this way shows that this event, which is a generating event for sigma of x1 through xn, is also clearly a generating event for the collection sigma of x1 through xn plus 1. Since all generators of the smaller sigma algebra are also generators, or at least members of the larger one, the inclusion holds.
Next, In section 2, we will study the properties of conditional expectation. We have a proposition: let x and y be random variables on our probability space omega script f p such that they are integrable, meaning the expectation of absolute x and the expectation of absolute y are both finite. Let script G and script H be event spaces or subsigma algebras of script F. Then the following statements hold true.
First, the identity property. If a random variable x is script G measurable and integrable expectation of absolute x is finite, then x itself is equal to its conditional expectation given script G almost surely. As a particular case, if C is any real constant, then C equals the expectation of C given script G. Now for the proof of the identity property, it follows directly from the definition of conditional expectation that x itself satisfies all three conditions. X is script G measurable by assumption. The averaging property expectation X indicator G equals expectation X indicator G holds trivially for all G in script G, and X is integrable by assumption. For the constant case, the event space generated by any constant function is the trivial event space containing just the empty set and omega. This trivial sigma algebra is a subset of any event space script G. Hence, the expectation of C given script G is simply C. Second property, linearity. The conditional expectation of a linear combination alpha x plus beta y given script G is equal to alpha times the conditional expectation of x given script G plus beta times the conditional expectation of y given script G almost surely. Let's prove the linearity. Let Z be defined as the conditional expectation of alpha x plus beta y given script G, and let Z1 be expectation x given script G and Z2 be expectation y given script G. We need to show that Z equals alpha Z1 plus beta Z2 almost surely. For part 1 of this proof, measurability, from the definition of conditional expectation, we know that Z1, which is expectation x given script G, and Z2 expectation y given script G are both script G measurable. Furthermore, the linear map G from R2 to R defined by G of x as alpha x1 plus beta x2 is a Borel measurable function. Therefore, the linear combination alpha z1 plus beta z2 is also script G measurable, as it's a Borel measurable function of script G measurable random variables. Continuing the proof of linearity, for part 2, the averaging property for any event G in script G from the linearity of regular expectation and the definition of conditional expectation, we have that the expectation of the quantity alpha Z1 plus beta Z2 all times the indicator of G equals alpha times the expectation of Z1 indicator G plus beta times the expectation of Z2 indicator G. Since Z1 is expectation X given script G and Z2 is expectation Y given script G, this becomes alpha times expectation X indicator G plus beta times expectation Y indicator G. By linearity of expectation again, this is equal to the expectation of the quantity alpha X plus beta Y, all times the indicator of G. For part 3, integrability, from the definition of conditional expectation, we know that the expectation of absolute Z1 and the expectation of absolute Z2 are finite. Therefore, using the triangle inequality, the expectation of the absolute value of alpha Z1 plus beta Z2 is less than or equal to the absolute value of alpha times the expectation of absolute Z1 plus the absolute value of beta times the expectation of absolute Z2. Since both expectation absolute Z1 and expectation absolute Z2 are finite, this sum is also finite. This implies that the random variable alpha Z1 plus beta Z2 satisfies all three defining properties of the conditional expectation of alpha X plus beta Y given script G. From the almost sure uniqueness of conditional expectation, we conclude that Z must equal alpha Z1 plus beta Z2, almost surely. Third property, monotonicity. If X is less than or equal to Y, almost surely, then the conditional expectation of X given script G is less than or equal to the conditional expectation of Y given script G, almost surely. Let's prove monotonicity. Let epsilon be any positive number and define the event A epsilon as the set of outcomes where expectation X given script G minus expectation Y given script G is strictly greater than epsilon. Since both conditional expectations are script G measurable, their difference is also script G measurable. So a epsilon is an event in script G. Then by the properties of expectation and the definition of A epsilon, we have that 0 is less than or equal to epsilon times the probability of A epsilon. This equals the expectation of epsilon times indicator A epsilon, which must be strictly less than the expectation of the quantity expectation X given script G minus expectation Y given script G times indicator A epsilon. By the averaging property of conditional expectation, this equals the expectation of X minus Y times indicator A epsilon. Since X is less than or equal to Y almost surely, X minus Y is less than or equal to 0 almost surely. Therefore, the expectation of X minus Y indicator A epsilon must be less than or equal to 0. Combining these inequalities, we have something positive being strictly less than something non-positive. This chain of inequalities, specifically 0 less than or equal to epsilon P. A epsilon which is strictly less than something less than or equal to 0 implies that the probability of A epsilon must be 0 for all positive epsilon. Taking the limit as epsilon goes down to 0, we get that 0 equals the limit as epsilon approaches 0 of P of A. Epsilon, by continuity of probability from above, this equals the probability of the limit of A epsilon, which is the probability of A0, where A0 is the event that expectation x given script g is strictly greater than expectation y given script g. Thus, this event A0 has probability 0.
Fourth property, conditional Jensen's inequality. If p psi is a convex function from R to R, and the expectation of the absolute value of p psi of x is finite, then psi evaluated at the conditional expectation of x given script g is less than or equal to the conditional expectation of p psi of x given script g, almost surely.
For the proof of conditional Jensen's inequality, we will use the fact that a convex function can always be represented as the supremum of a family of affine functions. Accordingly, we assume that for a convex function, psi mapping R to R, we have a set of linear functions phi sub I mapping R to R and constants C sub I for all I in some index set I such that psi of x is the supremum over I in I of phi sub I of x plus sub I. For each I in I, since phi sub I is linear, phi sub I of the expectation of x given script g plus c sub I is equal to the expectation of phi sub I of x given script g plus c sub I. This in turn is less than or equal to the expectation of p psi of x given script g, because phi sub I of x plus c sub I is always less than or equal to p psi of x. This follows from the linearity and monotonicity of conditional expectation. It then follows that p psi of the expectation of x given script g, which is p psi of the supremum expression, which becomes the supremum of phi sub I of expectation x given script g plus c sub I, is less than or equal to the expectation of p psi of x given script g. Continuing with the properties of conditional expectation. Fifth property, pulling out what's known. If y is a script g measurable random variable and the expectation of the absolute value of the product xy is finite, then the conditional expectation of xy given script g is equal to y times the conditional expectation of x given script g, almost surely. Now for the proof of pulling out what's known, from the almost sure uniqueness of conditional expectation, it suffices to show that the expression y times expectation of x given script g satisfies the three defining properties of the conditional expectation of xy given script g. These properties are 1. The random variable y times expectation of x given script g must be script g measurable. To the averaging property, the expectation of xy times indicator g must equal the expectation of y times expectation of x given script g times indicator g for any event g in script g. And 3 integrability, the expectation of the absolute value of y times expectation of x given script g must be finite. Part 1 is true because y is given to be script g measurable. Expectation of x given script g is script g measurable by its definition, and the product of two script g measurable functions is script g measurable, since the product function is Borel measurable. Continuing the proof for pulling out what's known. It suffices to show parts 2 and 3 primarily for simple script g measurable random variables y. Let y be of the form sum over y in script y of y times the indicator of E sub y, where E sub y is the event y equals y, which is in script G. We assume expectation of absolute xy is finite. For any G in script G, we have that G intersect E sub y is also in script G for all y in script y, and the union over y of G intersect E sub y is G. Part 2, the averaging property, follows from the linearity of expectation and the definition of conditional expectation of x given script G. Specifically, the expectation of y times expectation x given script G times indicator G can be written as the sum over y in script y of y times the expectation of indicator G intersect E sub y times expectation x given script G by the averaging property of expectation x given script G. This becomes the sum over y of y times the expectation of x indicator G intersect E sub y. This can be rewritten as the expectation of x times the sum over y of y indicator G intersect E sub y, which is precisely the expectation of xy indicator G. Part 3, integrability, follows from the fact that expectation of absolute xy is finite, and by applying the conditional Jensen's inequality to the convex absolute value function, recall that the absolute value of expectation x given script G is less than or equal to the expectation of absolute x given script G. Therefore, the expectation of absolute y times absolute expectation x given script G equals the sum over y in script y of absolute y times the expectation of absolute expectation x given script G times indicator E sub y. By conditional Jensen's, this is less than or equal to the sum over y in script y of absolute y times the expectation of absolute x times indicator E sub y. This sum is exactly the expectation of absolute xy, which we assume to be finite. Sixth property, the Tower property. If script H is a subsigma algebra of script G, so script H is contained in script G, then the expectation of the conditional expectation of x given script G, all condition on script H is equal to the conditional expectation of x given script H, almost surely. For the proof of the Tower property, from the almost sure uniqueness of conditional expectation, it suffices to show that expectation of x given script H satisfies the defining properties to be the conditional expectation of expectation x given script G given script H. These are one expectation of x given script H must be script H measurable. Two, the averaging property, the expectation of expectation x given script H times indicator H must equal the expectation of expectation x given script G times indicator H for all events H in script H. And three, integrability, the expectation of the absolute value of expectation x given script H must be finite. Part 1 follows directly from the definition of conditional expectation, which implies that expectation of x given script H is script H measurable. Part 2 follows from the fact that script H is a subset of script G, and hence any event H in script H also belongs to script G. Therefore, from the definition of conditional expectation, we have that the expectation of expectation x given script G times indicator H equals the expectation of X times indicator H. And by definition, again, expectation of X times indicator H also equals the expectation of expectation X given script H times indicator H. So the averaging property holds. Part 3 integrability follows from the conditional Jensen's inequality applied to the convex absolute value function. This gives us that the absolute value of expectation X given script H is less than or equal to the expectation of absolute X given script H. Taking expectations of both sides, the expectation of absolute expectation X given script H is less than or equal to the expectation of absolute X, which is finite by assumption. Seventh property, irrelevance of independent information. If a sigma algebra script H is independent of the sigma algebra generated by script G and X combined, that is sigma of script G comma sigma of X, then the conditional expectation of X given the sigma algebra generated by both script G and script H is equal to the conditional expectation of X given script G almost surely. In particular, if X is independent of script H, then the conditional expectation of X given script H is simply the expectation of X almost surely. For the proof of irrelevance of independent information, from the almost sure uniqueness of conditional expectation, it suffices to show that expectation of X given script G satisfies the properties to be the conditional expectation of X given sigma of script G and script H. The properties are: one, expectation of X given script G must be sigma of script G, comma script H measurable. 2, the averaging property, the expectation of expectation X given script G times indicator G prime must equal the expectation of X times indicator G prime for all G prime in sigma of script G comma script H. And 3, integrability, expectation of absolute expectation X given script G is finite. Part 1 follows because expectation X given script G is script G measurable by definition. Since script G is a subset of sigma of script G comma script H, expectation X given script G is also sigma of script G comma script H measurable. For part 2, it suffices to show the averaging property for events G prime that are intersections of the form A equals G intersect H, where G is in script G and H is in script H, as these generate sigma of script G comma script H. In this case, the expectation of expectation X given script G times indicator G intersect H equals the expectation of expectation X given script G times indicator H. Due to the independence of script H from sigma of script G and sigma of X, and thus from anything script G measurable like expectation X given script G times indicator G, this expectation splits into the product expectation of expectation X given script G times indicator G times the expectation of indicator H. The first term is expectation X indicator G. So we have expectation X indicator G times expectation indicator H. Again, by independence, this equals the expectation of X indicator G intersect H. Part 3, integrability, we've seen before. Expectation of absolute expectation X given script G is less than or equal to expectation of absolute X, which is finite. Eighth property, the L2 projection property. If the expectation of x squared is finite, so x is in L2, then zeta star defined as the conditional expectation of x given script g minimizes the mean squared error. Expectation of x minus zeta squared overall script g measurable random variables zeta for which expectation of zeta squared is finite. For the proof of the L2 projection property, we define L2 of script g as the set of all script g measurable random variables zeta such that expectation of zeta squared is finite. From the conditional Jensen's inequality applied to the convex function square x maps to x squared, we get that the square of expectation x given script g is less than or equal to the expectation of x squared given script g, almost surely. Since x is in L2, x squared is in L1. Taking expectations, this implies that expectation x given script g all squared is less than or equal to expectation of x squared, which is finite. It follows that zeta star defined as expectation x given script g is indeed in L2 of script g by the definition of conditional expectation ensuring its own integrability. We first show that x minus zeta star is uncorrelated with or orthogonal to all zeta in L2 of script g. Towards this end, let zeta be in L2 of script g. Consider the expectation of the product x minus zeta star times zeta. This is expectation of zeta x minus expectation of zeta times zeta star. Since zeta star is expectation x given script g and zeta is script g measurable, we can pull zeta inside the conditional expectation, the second term, the taking out what is known property, ensuring integrability via Cauchy-Schwarz. So it becomes expectation of zeta x minus expectation of zeta x given script g. By the law of total expectation, this is 0. Continuing the L2 projection proof, the expectation of x minus zeta star times zeta is expectation of zeta x minus expectation of zeta times expectation x given script g, which equals expectation of zeta x minus expectation of the expectation of zeta x given script g, which is 0. The above equality follows from the linearity of expectation, the script g measurability of zeta, and the definition of conditional expectation specifically, taking out what is known and the tower property. Since zeta star is in L2 of script g and we consider any zeta in L2 of script g, their difference zeta minus zeta star is also in L2 of script g. Therefore, based on the orthogonality we just showed, the expectation of x minus zeta star times zeta minus zeta star is 0. Now for any zeta in L2 of script g, we can write the mean squared error, expectation of x minus zeta squared by adding and subtracting zeta star. Expectation of x minus zeta star plus zeta star minus zeta squared. Expanding this and using the orthogonality property where the cross term expectation of cos minus zeta star times zeta star minus zeta is 0, or equivalently expectation of x minus zeta star times zeta minus zeta star is 0. This simplifies to expectation of x minus zeta star squared plus expectation of zeta minus zeta star squared. Since expectation of zeta minus zeta star squared is non-negative, the whole expression is greater than or equal to expectation of x minus zeta star squared. The minimum is achieved when zeta equals zeta star. And with this, we conclude our discussion on conditional expectations.